Have you ever played tug of war and felt that one perfect moment where nobody's moving? Or maybe you've wondered how a pilot can land a plane perfectly, even with a strong wind pushing from the side. Well, all of this stuff, it's about competing forces, pushes and pulls that are all happening at the exact same time. And in this explainer, we're going to pull back the curtain on the really elegant math that runs the whole show. Let's jump in. So, let's start with the big question, right? What really happens when two forces slam into each other? Now, you might think one just kind of overpowers the other, but it's way more interesting than that. The result is almost always a compromise, a brand new combined path that neither of the original forces was trying to make on its own.
Okay, to make this super clear, let's use a great example. Just picture a bird flying straight south at a steady 10 miles per hour. Simple enough. But now, imagine a 2-mile-per-hour crosswind hits it from the side. So, where does the bird actually go? Does it just get shoved sideways a bit? Does its speed change? This is the exact kind of puzzle that vectors were made to solve.
Now, before we can figure out our bird's final destination, we need to get our hands on the one essential tool for this job. It's called a vector, and trust me, it is the absolute key to understanding pretty much any situation where forces are competing.
So, what in the world is a vector? Well, it's way more than just a number. See, a regular number, a scalar, just tells you how much. But a vector, it tells you two things: how much and which way. Honestly, the easiest way to think of it is just as an arrow. The length of that arrow is its magnitude, its strength, and the direction it's pointing is, well, that's its direction.
All right, let's start with the absolute simplest thing you can do with a vector: just changing its strength. How do you make a force more powerful or less powerful? It's done with something called scalar multiplication. Now that sounds super technical, I know, but it's unbelievably simple. All we're doing is multiplying our vector's strength by a plain old number, a scalar. So if you multiply a vector by, say, 2, you've just doubled its power. That's it. The direction doesn't change one bit. It's kind of like turning the volume knob up or down on a force.
Okay, so we know how to make a single force stronger or weaker. But now for the main event. How do we combine two totally different forces? To do this, we're going to use a beautifully simple visual trick called the tail-to-head rule.
And this rule is exactly as simple as it sounds. You literally just follow the path. First, step 1, you draw your first vector. Let's say that's the bird's flight path. Then, step 2, right at the tip of that first arrow, you start drawing the second vector. That's the wind. The final combined result? That's just a brand new arrow you draw from your original starting point all the way to your final endpoint.
And this new vector, this sort of shortcut from start to finish, it has a special name, the resultant. Now here's the key insight. The resultant isn't just some third arrow we drew. No, it represents the single equivalent force that would give you the exact same outcome as the other two forces working together. It's the bottom line.
So, drawing the resultant is awesome for getting a feel for what's happening. But what if we need a really precise answer? What if we need to know the exact strength and direction of that combined force? For that, we're going to have to bring in some more powerful tools.
But before we jump into any formulas, I just love this piece of advice from our source, Mr. Wilfarth. He says to always draw the picture first. And this is such a key idea. The drawing isn't just a rough sketch for you. It's the map that shows you exactly what angles and what lengths you're even trying to find. It frames the entire problem for you.
And here it is. This is our power tool for getting that exact answer: the law of cosines. Now, I know the formula might look a little scary at first, but its job is actually pretty simple. It lets us calculate the exact length of our resultant vector, that's side C, as long as we know the lengths of the other two vectors, A and B, and the angle between them.
Okay, time to put it all together. We now have our complete toolkit. We can visualize any problem with the tail-to-head rule, and then we can get a super precise answer with the law of cosines. So I think it's time we go back and actually solve those puzzles we started with.
So, let's get back to our bird. Remember? Flying south, 10 miles per hour, getting hit by a 2-mile-per-hour crosswind. With our new tools, let's figure this out. How far does it actually travel in 1 hour?
We can set this up perfectly for the law of cosines. We know the bird's force, that's 10. We know the wind's force, that's 2. And we know the angle between them is 135 degrees. That's it. We have everything we need to find the real, true speed of that bird.
And after you run the numbers, the answer is about 8.7 miles. Now, stop and think about that for a second. The bird is flopping its wings hard enough to go 10 miles per hour, but it only actually covers 8.7 miles of ground.
That little 2-mile-per-hour wind didn't just nudge it sideways, it actually slowed the bird down. That is the power of vectors right there.
All right, let's try another one. So Elaine is walking her 2 dogs, Elvis and Ruby. They're both pulling, but in slightly different directions and with different amounts of force. So the question is, how hard does Elaine have to pull back on the leash to keep them all in check?
And just like with the bird, we just lay out what we know. Elvis is pulling with a force of 18 newtons, Ruby's pulling with 14. When we draw our little tail-to-head diagram, the angle inside our vector triangle works out to be 140 degrees. Now, all we have to do is plug those 3 numbers into the law of cosines. And what we find is that the dogs are pulling away with a combined resultant force of 30.4 newtons. So, for Elaine to keep them from running off, she has to apply that exact same force in the exact opposite direction. She literally has to become the equal and opposite vector. Okay, final puzzle. And this one has a really cool twist. You've got an airplane, it's flying at 400 miles per hour. A 30-mile-per-hour wind is blowing directly from the side. So, does that crosswind actually affect the plane's speed?
This is such a great question, because the answer is kind of both yes and no. See, the plane's engines are definitely pushing it through the air at 400 miles per hour. That's its airspeed, and that part doesn't change. But the wind is moving the entire chunk of air that the plane is flying in. So its speed relative to the ground, what pilots call its ground speed, that is the resultant vector of the plane's own thrust and the wind's push.
So, let's recap. You've just added 3 really powerful tools to your mathematical toolbox. You've got scalar multiplication to change a force's strength, you've got the tail-to-head rule to see how forces combine, and you've got the law of cosines to get that perfectly exact answer.
So now, you can see the world a little differently. Every push, every pull, every crosswind, it isn't just some random thing. It's a vector with a magnitude and a direction. You now have the tools to calculate the true path of a bird in the wind. Which, leaves one final bigger question. What unseen forces, what competing vectors might be shaping your own path through the world?